Okay, so we're going to actually try to solve this problem twice. The first try isn't going to be quite successful, but it gets a lot of the right ideas. So I'm going to let S0 be all the points, sorted by X. It's going to be sorted by X. I put things down here. And just to give you an idea where we're going, the array we're imagining here is first we'll write down all the points, then we'll write down some subset of the points, S1, then some subset of that subset, and so on until we get down to a constant size structure. Okay, first we write down all the points. Why? Because for dense queries, that's what we want. We want all the points just sitting there. So then you can just read through all the points, and dense queries will be happy. So if we detect a y-coordinate where the query is going to be dense, I don't know how we detect that, but let's not worry about it right now, then you could just look through S0. That's fine. But some queries are going to be sparse, and for that we're going to use S1, S2, and so on. The intuition is the following. If in your query the y-coordinate is very large, like say infinity, then your query is guaranteed to be dense. It doesn't matter what x is. Okay? And in general, if y is near the top, like it's at the topmost point, or maybe the next to topmost point, or maybe a little bit farther down, depends on the point set, then a lot of queries are going to be dense. So that's good news. Let's consider the first time when there's a sparse query. So we're going to let yi be the largest y-coordinate where some query, some x-coordinate, that y-coordinate, so this would be less than or equal to x, comma, less than or equal to yi, is sparse in Si minus 1. Okay, so initially we have S0, all points. Y1 is the largest y-coordinate where there's, so we work our way down until there's some sparse query in S0. That's yi. So then we just filter based on that. So throw away all the points above y, above yi. So we're going to say, take Si minus 1, intersect it with the range query, star less than or equal to yi. Okay, so the picture is we have some point set, and here, and it's some, up here, every possible query along this line is going to be dense because everything to the left of the x-coordinate will be in the output. At some point, we're going to decide, oh, this is too scary. There's a query here, maybe this one, or maybe it's this query that's sparse. And so we say, okay, let's throw away these points, redo the data structure from here down, ignoring all these points. Repeat, write down these things. So the idea is that if you look at a particular query, it will be dense in one of these SIs. And you can tell that just according to your y-coordinate. Because we said, oh, well, if you're up here in y-coordinate, you're guaranteed safe. So just do that search, and you're okay. In general, we continue this process until we get to some SI that has constant size. At that point, we're done. Then we can afford to look through all the points. Unfortunately, this is not a very good strategy, but it's a first cut, and it's close to what works. Here's a problem with it. Suppose you have this point set. Okay, what happens is, start at the top, everything looks fine. At some point you decide, oh, there's a query here, namely this one, which has an empty answer, and yet there are points to the left of this x-coordinate, right? So that's bad. Because 0, it's very hard to get within a constant factor of 0. So pretty much immediately you've got to draw a line here and say, okay, S0 is all points, S1 is these points, S2 is going to be these points, In general, they're suffixes of the points, and so the total space will be quadratic. Okay, so the first two properties will be correct, because you're just looking in S0 or S1 or whatever. Everything looks fine, but your array does not have linear size. So, no good. First try failed. Second time's a charm. So, need a little more sophistication in how we do this partitioning, how we build our array, and we'll get it. I have written here, I didn't read this before, this one line. It says maximize common suffix. I have no idea what this means, but maybe it will mean something by the end. Let's see. Okay. Here, this is the part I read. So xi is going to be, so we had a yi. That's going to be the same as before. This is why I did the first attempt. This definition remains the same. So largest y, where we have some sparse query in si minus 1. Okay? I want to look at what that x coordinate is. Here it says there's some x. What is that x? Let's just look at the maximum possible x that it could be. This will turn out to be really useful. Maximum x coordinate where less than or equal to xi, comma, less than or equal to yi is sparse in si minus 1. Okay, we know there's something we can put in here that makes yi sparse. So look at the largest possible such x. So that means any query, so we have this new point. It's not an actual point in our problem, but it's a query, xi, yi. And it's dense, or sorry, it's sparse, it's bad. We know that any query up here is dense. That was the definition of yi. And now we also know that any query over here, I guess, not saying a lot, but these queries are also dense. Because again, if you're far enough to the right, that's going to be basically everything. So let's get rid of that as well. And this is a problem. Queries over here are also potentially a problem. We don't know. Okay, it doesn't seem like much, but it will be enough. We're going to redefine si as well. So here's the fun part. If we have some si minus 1, we're going to define a new thing, which is pi minus 1. Which is this. Okay, this is a funny thing, but it is this part of the point set. This is pi minus 1. So the points we care about are kind of here, but let's just take everything to the left of this x coordinate. Why not? It's a thing. Okay, that is pi minus 1. So si minus 1 is everything in this picture. And we're now just, first let's restrict to x, then the next step is we're going to restrict to y. But it's in a funny way. So this is the si, the next S set. Take the previous set, we intersect it with a funny thing. It's harder to write algebraically than it is to draw the picture. So it's intersected with a union, which is basically, dare I draw it on the same picture? There's my red here. It's going to be less than or equal to y. This thing is going to be si. Okay, we'll see why eventually this works. I still don't know what maximize common suffix means, but we'll get there. So we're looking at the points below the line. That's what we did before. We used to say SI is just the intersection with less than or equal to YI. But things are just a little bit messier because of this restriction. Do I really not have a P here? Okay. Here's the difference. The reason we have to go through this business. The array that we're going to store is not the SIs. The SIs are still too big, potentially. What we're going to store are the PIs. PI minus 1. And then in the end, we're going to store SI. SI, again, has constant size. The final SI has constant size. Probably should have used a different letter, SK or whatever. But we keep doing this until we get down to something constant size, then we store it. That's the easy case. Until then, we just store the PIs. Because really, I mean, we know that all the queries up here and over here are OK. They're nice and dense. We sort of only care about the points to the left of the line. Okay, but that essentially the SI has to pick up the slack. And we have to include these points in the next SI, whereas before we did not. Before we just took things below the line. Now we have to take things that are below the line or to the right of the vertical line. Okay, this is essentially necessary for correctness. So we kind of win some, we lose some, but it turns out all is well. So I know this is weird, but let's jump to the analysis, these claims, in particular that the array has linear size. Let's think about that, and it will become clear why the heck we made these choices. Let's see, I have a question first. No, this definition of SI is no longer in effect. S0 is correct, and all the SIs are still sorted by X. But yeah, we're no longer doing this. Instead of this rule, we're doing this rule. So it has, this part is the same, but we have this extra union, which contradicts the previous rule. So the YI definition is the same. Sorry, it's a little weird. XI is new, PI is new, and SI is new. Okay. At this point, it's this algebraic weird thing. But here's the cool thing. For the spacebound, claim is PI minus 1 intersect SI is less than or equal to 1 over alpha times PI minus 1. Okay, this is hard to even interpret what it means, but it's good news. So remember, alpha is a number bigger than 1. It's what we use in the definition of density. And you can set this parameter whatever you want. Say 2. Okay. So then we're going to get that this thing, whatever it is at most half the size of the previous one. Okay. I claim this is good news. I claim it means that these PIs essentially are geometrically decreasing in size, which is how we get. It's not literal. That's not quite right, but this will give us a charging scheme, which will prove that the whole thing has linear size. Okay, first, why is this true? It could really only be true from sparsity, from the alpha, right? So we said, oh, density is good. If we have dense, there's nothing to do. It's just put the points in X order, we're done. Sparse is bad, but actually sparse tells us something. It tells us there are a lot of points that are not in the answer. So we're looking at this query, xi, yi. Right? We'd like to just say, oh, start at negative infinity and just take all the points up to here. If we're dense, that is within a constant factor of the number of points that are actually in the answer, which is down here. If we're sparse, that means there are a lot of points up here. most of the points have to be up here in order to be sparse. Okay? And that's actually what this is saying if you expand the definitions. So pi minus 1, that was all the stuff to the left. Okay, so that's this thing. This is what we would get if we just did a linear scan from left to right. Versus, we're considering the points in pi minus 1, which just restricts to x, and then we're looking at SI. SI does, this business, but if we restrict to the SI points that are to the left of the line, so we're looking at basically this left portion, which was this white rectangle, intersected with this funny red rectangle, which was kind of awkward. But the intersection is just this. That's the answer for this query, xi, yi. Okay, so this is the size of the answer for xi, yi. Okay, and this was the number of points left of number of points in less than or equal to xi star. We wanted to just do a linear scan like this, but this is the correct answer. And because we know that this point is sparse, that was the definition of xi and yi, it was the maximum sparse point, so it's a sparse point. Therefore, we know that this does not hold. So the number of points less than or equal to x comma star is greater than alpha times number of points in the correct range. And if I got it right, that should be this. I could put alpha over here without the 1 over. And I guess this is strictly greater. No big deal. Okay, so that's the definition of sparsity. So this is the cool thing we know. Now, we're going to use this. This is now a number less than 1. Question?
So for pi minus 1, you have that it's the number of points less than xi star. But like, for example,
Yes, that's the definition here.
One like pi, you don't have that block in the top left corner, right?
Right. After we restrict to SI, yeah, we've thrown away all of these points.
Right. So if you take like the next pi, it's not necessarily going to be the points less than or equal to xi.
It's true. When I say points, I don't mean all points. I mean points in SI minus 1. In fact, I'm dropping that because it gets awkward to keep talking about. So that's a correctness issue, essentially. You have to argue that we can throw away these points and it's safe. Once we do, then you just ignore their existence. And because, you can ignore their existence because you already solved all the dense queries which are over here or over here, which involve those points. And so we now know that we're only going to be doing queries from here down. And so otherwise you look at P0. So forget about those points. Now you're going to be searching in one of these structures, so you can forget about all the points over here. So that's that argument. Now, once you've restricted to SI minus 1 and you don't have to look at any other points, among those points, this is going to be all the points less than or equal to xi. But that's how we were defining sparse, right? We said sparse in SI minus 1. So it's among those points, we have sparsity. So this is the definition of what we have. Okay, the claim is it's a good thing. Here's a charging scheme. So this is by sparsity. So I'm going to charge storing pi minus 1 to pi minus 1 minus si. This algebra I have to interpret every single time, but that's fine. Let's look at the picture. Okay, pi minus 1, remember, was this white rectangle here. Everything to the left of the line. So now we have to store pi. So we want that the sum of the sizes of the pi's is good. And so here's my charging scheme. We have to store pi minus 1. I'm going to charge it to these points. What are those points? Those are the points that are inside the white rectangle, but outside the red L shape. So that's these points. This is pi minus 1 minus si. Those are the points that I'm throwing away. That's good. If I charge them now, I will never charge them in the future, because I just threw them away. They're not in the next si. So each point overall in the point set only gets charged once. Okay, how much does it get charged? How do these things relate to each other in size? That's where we use this thing. It gets confusing to think about intersection versus difference, but the point is, we look at the pi minus 1s that are in SI, that's a small fraction. Think of alpha as 100. So then the pi minus 1, so this part down here that's in SI, this is only 1/100th of the whole white rectangle. So that means this part is 99/100ths of the pi. So if we charge the storing of the entire rectangle to these guys, we're only losing a very small factor, like 100 over 99 or something. It is actually exactly 100 over 99, I believe. I worked it out, and the factor of charging, assuming I did it correctly, is 1 over 1 minus 1 over alpha, which works out to alpha over alpha minus 1. It doesn't really matter, but the point is it's constant. Okay, I think that's easy to believe. Maybe it's actually easiest to think about when alpha is 2. So then, at most half the points are here, at least half the points are here, and so we're storing the entire point set to these points, which will never get charged again, so we're only charging with a factor of 2. That's all we need, constant factor. Okay, therefore, this thing has linear size. That's the cool thing. We get more, though. We also get the query bound we want. Let's think about the query bound. So, this is fun. Think about where the query is. It used to be, over here, we do a search in S0, or we do a search in S1, or we do a search in S2. We'd never look at multiple SIs, because there'd be no point. Either S0 was dense and we're fine, just do it, or you have to jump to S1, skip some guys up top, do a search in there, fine. We no longer have that luxury over here because we're using PIs instead of SIs. So it actually may be a search starts in P1, but then has to go through P2 and has to go through P3. But it's okay, because the farther we go right, we have this sparsity condition that tells us basically the points we're looking at are, the number of points we're looking at are getting smaller and smaller. So I'll wave my hands a little bit here, but the claim is it's a geometric series. This needs a formal proof, but I won't go through it here. Decreasing, so this is the query bound. The number of scanned points is order output size. So you have to check that no matter where you start in PI, that's a little bit tricky part. We're not looking at all of PI. We're looking at some of PI, and then we're going to the right from there. Actually, is that true? Maybe we always look at all of PI. Think about this. I think we do, actually. So, sorry. That's what we did before. So, we basically figure out where we are in Y coordinate. That was the overall structure. We had a Van de Boa search tree on Y. So all we know at this point is the Y coordinate of our search. And so we use that to determine which of the PIs we go to based on sort of where the YI becomes no longer dense. And then we're going to have to search through that entire PI and potentially more of them because this is no longer an SI. It's just doing the things to the left. And so, if we're lucky, the PI we're looking at, or the query we're doing, is not to the right of this point. Okay, maybe it's right here. That would be great. Then all our answers are done. We know if our query is here, that would have been dense, so we would have done it in an earlier stage. Our query might be down here, though. Okay, when the query is down here, we need to report on these points. Then we're going to have to do more. That's going to be PI plus 1. And so we'll do more and more PIs until we get to our actual query here. Okay, but in any case, the claim is that this is geometrically decreasing by the same charging scheme. Okay, that's 2 out of the 3 claims. There's one more. which is closely related. It's still about the query problem. What we haven't shown is that we actually find all the points. This is what you might call correctness. To prove this, what we need to say, what we claim, is that after you do the P1s, and now you do the now you do the P2s. Well, I'll tell you. The claim is that you visited some x coordinates here. The PIs were all the things up to some x coordinate. Claim that the very next point in here in P2 has a smaller x coordinate than what you just did. Okay, I think that should be clear. I mean, because presumably there are some points in here. And so the very next PI, it's restricted within this red thing, but it's going to be up to some x coordinate. So you're basically starting over. Every time you go to the PIs, you're starting over an x. Go back to minus infinity and x. So the idea is the picture will look something like this. You start at minus infinity, you read some points. At some point, you run out of the PIs. Then you start over again. You read some smaller set of the points. Maybe you get a little farther. Start over again, read a little farther. At some point, you're going to reach your threshold x. That's when you stop. So that's correctness. It's unbelievable. I feel like I need another sentence there. Right. Once your PI encompasses your x range, that's going to have your answer. Then you're done. So that's this moment. And so the only worry is that an early PI basically, or maybe the next PI does this, and then we do this, or something like this. That never happens basically because you're always resetting x range. And so your x will always start over to something less than what you had. And so the termination condition, which I probably didn't write down here, but which is, stop when your x coordinate is bigger than what you want, never terminates early. Therefore, we get all the points we care about. Okay, a little bit hand-wavy, but that is why this structure works. It's a very weird setup, but linear size, and you just jump into the right point in the array, start reading, throw away the points that aren't in your range, because they just happen to be there. Those would be these points up here. Throw away duplicates. Just output the points in your range. And it gives you magically all the points in here by a linear scan. I still find this so weird. But it's true. Truth is stranger than fiction, I guess. Other fun facts. You can actually compute this thing in the sorting bound. So pre-processing is just sort. I won't prove that here. So this was two-sided. Let me briefly tell you how to solve three-sided and four-sided. I mean, we basically already did this one, which was, I'll remind you what it looks like. So you have a binary tree, and on each node, you store two augmented structures, one which can do range queries like this, and one which can do inverted range queries like this. This should look familiar. And so you do a search on, let's say we want to do this thing. So we have x1, x2, y2. You search for x1, you search for x2, find the LCA, and then in this subtree, you do a search. Right, in this subtree, you already know that you're less than x2, and so you do the x1 y2 search in this node, and then in the right subtree, you do the x2 y2 search. You take the union of those two results, and that is this query. Right? That's how we did it before. No difficulty here. And the point is, in this world, you can build this, put it in a Van Emden-Bos layout. You do this search, you do this search, you find the LCA in log base B of n to check that everything works cache obliviously. Then these structures are just structures which we already built. And so, yes, we lose a log factor because every point appears in log data structures, but that's it. everything else works the same. So we get n log n space log base b of n plus output over b query. Because now we just have to do 2 queries instead of 1. We don't lose a log factor. That's the trick we did before. Okay, that was easy. One more. So that was 3-sided. Next is 4-sided. Four-sided, of course, we could do exactly the same thing, lose another log factor in space, maintain log base b of n plus output over b query time. But I want to do slightly better. And this is a trick we could have done in internal memory as well. But I have 2 minutes to show it to you. So here bonus. Didn't have to do this in external memory context, but we can. 4-sided. So we're going to do the same thing, but not on a binary tree. Take this binary tree. This is sorted by x, I suppose. This is keyed on x. Instead of making it binary, make it root log n array. So imagine taking the binary tree, taking little chunks which have size square root log n, capital N, and imagine contracting those chunks into single nodes. So we have a single node which has square root log n children. Another node has square root log n children. Okay, this is all static. And so on. Otherwise, the same. The augmentation is going to be a little bit different. Okay, if we look at a node, we're going to store the same things we had before, which was this kind of query and this kind of query. We're going to store a little bit more. Namely, for any interval of children, like here you have some start child and some end child, I want to store for all the points that are down there, for this thing, store a regular binary search tree on y for those points. Why? Because if we do a search, okay, same deal, we find the LCA of x1, I don't know. Let's say it's on x. We'll have to do it again on y, whatever. So here's the LCA. Let's say there's a lot of children. Okay, maybe here is x1, and here is x2. Okay, so in this subtree, we do this. We do this range query, because we want to go from x1 to infinity. Over in this subtree, we want to do this range query, because we want to go from infinity, negative infinity, to x2. But then there's all this stuff in the middle. I don't want to have to do a query for every single tree. Instead, I have this augmentation that says for this interval, here are all the points sorted by x-coordinate, I guess. I'm doing it this way. Fine. So then it is a range query. I mean, I want to know what are all the points. Wow, this is confusing. I feel like I've missed something here. No, this is on y. Sorry. These points I've got sorted by y, so I should draw it the other way. Right? These points we already know are in between x1 and x2 in x. We've already solved the x problem here. So now I just need to restrict to the y range from y1 to y2. In these trees, these already match in x. I just need to make sure they match in y. So I do a regular 1D range tree. I search for y1, search for y2, take all the points in between. This is cheap if I just have a regular old binary search tree. Now this thing has linear size. This thing has, I think I actually need, I should have a 3-sided range query. Thanks. These should be 3-sided. Because here I know that I've got the right side covered already in this tree. I've got the left side covered already in this tree. but I still need the remaining 3 sides. In here, I only need these 2 sides because I've already got x1 and x2 covered. Okay, so this is cheap. I only need a linear space data structure. This thing is not so cheap. I'm using the previous data structure, this thing, which has n log n size. These are 3-sided range queries. Sorry for drawing it wrong. Okay, so I need 2 3-sided structures. Then I need actually a whole bunch of these structures because this was for every interval. But conveniently, they're only log n intervals because there's root log n children. So root log n squared is log n. So there's root n, but then we need log n of them. And so that's what these things balance out, as you see. So normally, this would be n log squared n because every point would appear in log n trees. But now, the height of my tree is merely log n over log n with a factor 2 out here because I have a square root here. Okay, so tree has height log n over log n, so each point only appears in log n over log n structures. Each of them needs a structure size n log n, so we end up with n log squared n over log n space. Kind of crazy. But this is how you get that last little bit of log n space improvement by contracting nodes, doing a simpler data structure for these middle children, and just focusing on the left child and the right child. You have to do one 3-sided call, but then the middle is a very simple 2-sided call. It's just a 1D structure, and so it's really cheap. That's it.